Let's take a look at a couple of trigonometric functions where we need to use the chain rule to find the derivative. So we'll take a look at 4 examples in this video. Here I have y equals cosecant of theta cubed. The first thing to note is if you're used to working with x, well, theta is the new x. We can have functions of angle, polar functions, and it doesn't change anything, we just have a different letter. So here we're composing two functions, doing two things in sequence to theta. First I'm cubing it, and then I'm taking the cosecant. You might not see cosecant that often. Cosecant is just 1 over sine. And we could use the power rule in some algebra to show that the derivative of cosecant is cosecant cotangent. We'll use that here. So there are our two parts that require us to use the chain rule. So like I said, we'll take the derivative of the outside, knowing that cosecant, the derivative is cosecant cotangent. What do I mean by that? It's cosecant of the thing inside times cotangent of the thing inside, where cotangent is 1 over tangent. And remember what happens to the inside here? It stays the same. A little bit exotic, because staying the same, it now appears in two places. And now we multiply by the derivative of the inside. What am I saying here? This was a cube. So what is the derivative of theta cubed? 3 theta squared. And there is our derivative. Next example, here we have cosine, a much more familiar trig function. That's the outside function. And what do we usually do when we have a root of the variable? We're going to rewrite that as a fractional power. Here it's a cube root, so I'm doing a 1/3 power. What is the derivative of cosine? I remember that it is negative sine. Inside stays the same. And now we multiply by the derivative of the inside. Here we have theta to the 1/3. If I subtract 1 from 1/3, I'm going to get a negative 2/3. So we will have times 1/3 theta to the negative 2/3. And our work is done. Let's take a look at another example. Here we have some notation that's kind of terrible, but it is traditional, so I know that you'll see it. What this means is 4 times sine of pi theta squared. It might look like it means sine of pi theta. That is not what that notation means. So we're going to use the power rule here. Notice that we're taking 4 times a thing squared. That is our outer function. Inside that we have taking the sine of the function, and inside the inside I have multiplying by pi. So those are the 3 things we're going to need to chain rule here. So y prime will be, first we do the outside, we're going to bring that 2 down. Power reduces by 1, so I could remind myself by putting the 1 there. Inside stays the same. Inside of the inside stays the same. And now we multiply by the derivative of the next layer inside. So derivative of sine is cosine. Inside stays the same. Let's make that theta look a little bit better. And now times the derivative of the inside, which is just pi. You could think of this like what's the derivative of 3x is 3. Derivative of pi theta is pi. So we can bring that 8 and pi together, writing them out front, like we usually do with constants. 8 pi sine of pi theta times cosine of pi theta. One last example. Here we have a polynomial term. Well, it's a monomial here. Put inside a cosine. Put inside a sine. I'll admit I don't often put trig functions inside trig functions in applications like in physics, but it is a good exercise here. So let's identify our parts as usual. We have sine is the outside function, cosine is the next layer in, and finally the third layer is 4x cubed, which I know is 2 things. We're cubing and multiplying by 4, but I think we can handle that. So to take the derivative, we're taking the outermost layer. Derivative of sine is cosine. And what happens to all that junk? It stays the same. And now times the derivative of the next layer in. What is the derivative of cosine? Derivative of cosine is negative sine, and the inside stays the same. And now I multiply by the next layer in, so this is times derivative of the inside here would be 12x squared. And that is it for that function.